Now let us move on to the third question. So the third question was asked in IIT Delhi. So I got this question from one YouTube video. I'm sharing it here because the answer given in that video was not satisfactory. And I think that this is an important question. You will get a lot of concepts from this question. So I'm sharing it here. The question is like this. Consider a monovalent (1D) lattice. So will it be metal or insulator? So this was the question. We have to consider monovalent 1D lattice. Will it be metal or insulator? Before answering this question, I want you to understand certain things. The thing is that whenever an electron is in a stationary state, that is eigenstate, whenever an electron is in a stationary state or eigenstate, its expectation value of position is 0. You can take the eigenstate of any system. When an electron is in an eigenstate, stationary state, its expectation value of position will be 0. What that means is that there is no effective movement of electron from one place to another. Electron is not moving. So when electron is not moving, then it is an insulator. When electron is not moving, that is expectation value of position is 0, then effectively electron is not moving. Then it is an insulator. Only when electron is moving, it is conducting. Current is there, right? Only when there is a motion of electron from one place to another, there is current flowing in a material, then only it can be called as a conductor. So for electron to move from one place to another, its expectation value of position should not be equal to 0. For that, electron should be in a superposition of eigenstates. Only when electron is in a state which is superposition of many eigenstates, then only expectation value of position becomes non-zero. Then only it can move from one place to another place. Then only it can be called as an conductor. So this is the concept that I want you to keep it in mind. So to learn more about these things, you can watch a MIT lecture that I have attached in my description box. Now let us get back to the main question. Let us consider a monovalent 1D lattice. So if you have read the chronic penny model, you would have noticed there are two types of representing the EK diagram, the band diagram of a solid, the extended zone scheme and reduced zone scheme. So I am using a reduced zone scheme here. Then it is like this. So there are many bands above that like this, like this. So there are many above. We have to only consider this now. Suppose there are n monovalent ions present in the 1D lattice that we are considering. So 1D lattice looks like this, right? So these are the monovalent ions. It can be Na plus or lithium plus. Can be any monovalent ion. I'm taking Na plus. Okay, we are considering n ions. So if there are n ions, then there will be n states. Why there are n states? The reason is that for analogy, consider two electrons, one with upspin and one with downspin. So when these two electrons couples, there will be two states possible, both along the same direction, like this or like this, or one spin opposite to another, like this or like this. So when they are not coupled, there will be only one state, right? Only one energy state for the electrons. The energy of the electron when it is isolated from each other. Then when both couples, the number of states of the overall system becomes 2. This state having a higher energy compared to this state. So similarly, when two ions interact, so this is the nucleus of one ion, and this is the electron cloud, and another ion, and its electron cloud. So there will be repulsion between the nucleus, there will be repulsion between the electron cloud, and there will be attraction between this nucleus and the electron cloud of this ion, and there will be attraction between this nucleus and the electron cloud of this ion. So due to these interactions, the energy level of the overall system becomes 2. For example, if you consider a particular energy state, for example, 2p. So here also 2p. That 2p energy level becomes 2 due to these interactions. The energy level of the atoms, the overall system, becomes 2. Similarly, if there are n ions, then the number of states becomes n. There will be n states. So here there will be n states along this curve. Okay, each point is a state. Okay, and there will be n states. In each of those states, 2 electrons can be accommodated. One Na plus contributes 1 electron. So if there are n ions, there will be n electrons, and there are 2n states. There are 2n states. Why 2n state? Because n ions are there, then there will be n states. Due to the interaction between the ions, the number of states becomes n. So this curve contains n states. Each state occupies 2 electrons. So there will be 2n states that can be that is available for electrons. So there are 2n states, but n electrons, right? Because each Na plus contributes 1 electron, so there are n electrons and 2n states available for them. So this n electron occupies n states. So from here to here, it is occupied. N states out of 2n states are occupied by the n electrons. Then all the states available here are unoccupied, right? Here, the electrons are not there here. Only electrons are present along this region. So electrons present here at these regions. The electron here can exist in a state which is superposition of more than one excited states. Okay, more than one excited states. Here also, electron can exist in a state which is superposition of more than one excited states. So as I said earlier, when an electron is in a state which is a superposition of more than one states, then the expectation value of position of that electron is not zero, which means electron is effectively moving from one region to other region, then the material can be said to be a conductor. So therefore, here we can say that this 1D monovalent lattice is that of a conductor. So it is a conductor here. So if you want to learn deep about these things, you can watch the MIT lecture that I provided. And now let us move on to the next question, which is related to the first question. So the next question that have been asked is, the next question that was asked is 1D lattice of divalent ions. So here also we can draw the reducible zone scheme. E A. So here we are considering a 1D lattice of divalent ions like calcium 2 plus, calcium 2 plus, like that. Then if there are n ions, as I have already said, there will be n states due to the interaction between the ions. Each state occupies 2 electrons. So there will be 2n states here, 2n states along this curve available for electrons. Now, each ion contributes 2 electrons, gives away 2 electrons. So there will be 2n electrons. Therefore, all these states will be occupied. All these states will be occupied because there are 2n states and there are 2n electrons. Each electron occupies each states of that 2n states. So the 2n states will be occupied. Now, if the electron have to be in a state which is a superposition of more than one excited states, then the electron have to go from here to the next band. For that purpose, we have to give a certain amount of energy. Depending on the amount of energy that we are giving, if we are giving a huge amount of energy for the electron to go from here to here to be in a state which are superposition of more than one excited states, then it is an insulator. If we are giving a moderate amount of energy of the order of electron volts, then it is a semiconductor. So this is how we distinguish between metal, that is conductor, insulator, and semiconductor. So here we can see that we have to provide an amount of energy, certain amount of energy for electron to move from here to here. But in the previous case, for electron is already filled, electron is filled up until here, right? So for electron to be in a state which is a superposition of more than one excited state, the energy required is very, very, very small. So with small amount of energy, even the thermal energy available for room temperature is sufficient for the electron to be in a state which is a superposition of more than one excited states. Then it is a metal, right? Only small amount of energy is needed for electron to go to a next state which is a superposition of more than one excited states. Then it is a conductor. But here, for electron to go to a state, next available unoccupied state, we have to provide energy. So it is an insulator here. As the question asked is whether it is a conductor or insulator, here we can say it as insulator. So this is insulator. Now let us go to the next question. The next question asked was 2D lattice of monovalent ions. 2D lattice of monovalent ions. So here it is a 2D lattice. Now let us draw the reducible scheme representation. Ka here, and there is energy. Now, you know that looks like this. But here, for 2D as well as 3D case, we cannot draw the second band here because depending on the nature of the material, the bands can overlap. But 1D, for 1D case, it is sure, it is 100% sure that bands will not overlap. But for 2D and 3D case, depending on the type of material, bands can overlap, which means that the bands can be like this. Bands can overlap. So even though here also we can use the same logic, there are n ions, which means n states. Each state can occupy 2 electrons, so there will be 2 n states available for electrons, and there are n electrons. So this n electron occupies the n states available. So out of the 2 n states available, only n states, half, are filled. So electron can exist in a state which are superposition of more than one excited states, which means this is a conductor. This is a conductor. 2D lattice of divalent ions. We can draw the reducible scheme. As it is a 2D case, the bands can overlap. The extent of overlapping depends on the type of materials. So here, if you are considering n ions, there will be 2 n states available for electrons, and there are 2 n electrons as well. There will be 2 n electrons as well because each ion contributes 2 electrons as it is a divalent ion. So all these states here, present here along this curve, are occupied. But as the bands are overlapping, electrons, depending on whether it is overlapping or not, as I have said, the nature of overlapping, whether it overlap or not, depends on the type of material. It can overlap here or it cannot overlap. It will not overlap depending on the type of material. But for 1D case, it is sure that there will be no overlapping of bands, but it is not for the case of 2D lattice. It can overlap or it will not, depending on the type of material. So we cannot say whether it is a conductor or insulator. If it is overlapping, electron can easily go from here to the available next state, which is a superposition of more than one excited state, so that the electron can conduct. Then it will be a conductor. If it is not overlapping, For certain materials, it will not overlap even if it is 2D case, then it will be a insulator. So we cannot conclude whether it is a conductor or it is an insulator if it is a 2D lattice of divalent ions. Same logic can be applied for the 3D case also. For 3D lattice of monovalent ions, there will be n ions, there will be 2n states available for electrons, but there will be only n electrons. So there we can say that for 3D case, for monovalent case, it is sure that it will be conductor or metal. We can also say it can be metal or metal, okay? So here also, here it is so monovalent 1D lattice, it is a conductor. We can also say that it is a metal. Here also 2D lattice of monovalent ions. It can be conductor or metal. 3D monovalent case can be, it is conductor or metal. It is 100% sure that it will be conductor or metal. But divalent case, depending on the type of overlapping, whether it will overlap or not, depends on the nature of material. So we cannot say whether it is a metal or insulator. So here for 2D lattice of divalent ions, this case also we cannot say whether it is a metal or insulator. Now let us move on to the fourth question. So this question was asked in IIT Bombay. The question is like this: we are considering a semiconductor and we all know what is Hall effect. A current is passed along the x cap, positive x direction, and magnetic field is applied along z direction. And we all know that Hall voltage will be developed across the y direction. So the question is, where will the electrons and holes get accumulated? Here, we know that when current is flowing along the positive x direction, electron will move along the negative x direction. So applying the formula, Lorentz formula, force formula, F is equal to Q into V cross V. Here charge of electron is minus E and velocity of electron is along minus x cap direction and magnetic field is along z cap direction, along z axis. Then this minus and this minus gets cancelled, then we will get EBV into x cap cross z cap. X cap cross z cap is minus j cap. Then we will get like this, minus EBV j cap, which means that the force acting on the electrons will be along minus j cap direction. So electrons will get accumulated at the lower surface of the solid. Electrons will get accumulated at the lower surface of this solid. Now let us move on to the holes. Force acting is equal to Q into V cross B, where the charge of hole is E, plus E, and electrons will move along the negative x direction, whereas holes move along positive x direction. The direction of holes and the current is same. So the velocity is along x cap. So EBV x cap cross z cap. So x cap cross z cap comes as minus j cap. So here also the force acting on holes is also along minus j cap direction. That is along the negative y-axis. So holes also get accumulated at the lower surface of the solid. So electrons as well as holes gets accumulated at the lower surface of the solid. So the next part of the question is, so how do we distinguish between an N-type semiconductor and a P-type semiconductor using Hall effect? We know that when we place a semiconductor, both electrons and holes are getting accumulated now at the lower surface of the solid. So how to distinguish between the n-type semiconductor and p-type semiconductor? That the answer is that even though electrons and holes are getting accumulated at the lower surface of the solid, the amount of electrons and the amount of holes that gets accumulated at the lower surface is different for n-type and p-type. For n-type, the electrons, the amount of electrons and the concentration of electrons that gets accumulated at the lower surface is greater than that of holes, whereas for p-type semiconductor, the holes will be more than the electrons at the lower surface of the solid. So we can use this concept to distinguish between n-type and p-type semiconductor. I will explain it now. To experimentally distinguish the n-type and p-type semiconductor using the Hall effect, we should connect the multimeter. You would have seen multimeter, right? In lab, there will be digital display and there will be two wires, red and black, red from positive terminal and black from negative terminal. So we have to connect these terminals on the semiconductor that we are observing. The positive terminal should be connected here and the negative terminal should be connected here. And if it is an n-type semiconductor, then the number of electrons getting accumulated at the lower surface will be greater than the number of holes. So then if electrons are more, the amount of electrons are more, then we will get a negative potential reading in the multimeter, which shows that it is n-type. Now, if it is a p-type semiconductor, at the lower surface, the holes will be greater than the number of electrons, which means holes will be greater, which means we will get a positive reading. Which means it is a p-type. So in this way, we can distinguish between the n-type and p-type semiconductor using Hall effect. So why it is happening? When electrons are more, here the charge will be negative and here it will be positive. Then the reading, as the positive terminal is connected at the lower end, as electrons are more here, then we will get a negative reading. But if the holes are more here, the lower surface have a positive potential with respect to the upper surface, then we will get a positive reading in the multimeter. So in this way, we can distinguish between n-type and p-type semiconductors using Hall effect. Here the value we are getting at the multimeter, that the potential difference is basically the Hall voltage itself. One more thing I want you to know is that Hall effect is used for measuring magnetic field. There are many Hall sensors which are made for measuring magnetic field. So how the magnetic field can be measured using Hall effect? The answer is simple. We know Hall voltage is given by magnetic field into current by NEW, where N is the charge carrier concentration, E is charge of electron, and W is width. Width is here. This is width. Width is always measured along the direction of magnetic field in this type of arrangements. So now here, magnetic field can be isolated here. When we write magnetic field like this, magnetic field is given by NEW, Hall voltage by current. Here we have to find N, right, charge carrier concentration. For that, what we can do is that here, if you are keeping the current passing through the semiconductor as constant, if you are keeping the current constant, then EW is already constant. Then what we can get is Hall voltage is directly proportional to magnetic field. Okay, Hall voltage is equal to I by NEW into magnetic field. So this, I'm taking it as a constant. Hole voltage is directly proportional to magnetic field. When the current passing through the material under consideration is kept constant, then hole voltage is directly proportional to magnetic field. So when we plot hole voltage for different magnetic fields, by varying magnetic field, we are recording hole voltage. Then as it is directly proportional, we will get a straight line whose slope, when we measure, will be equal to I by NEW. So from this slope, N can be found out. Okay, charge carrier concentration can be found out. So to measure the magnetic field, we can use this formula NEW hole voltage by current. So here, to get charge carrier concentration N, we can do some graphical work. Hole voltage is directly proportional to magnetic field. When the current passed through the material is kept constant, then that slope of the line that we got by measuring the hole, okay, this is H here. Hole voltage, by measuring the hole voltage at different magnetic field, the slope is equal to current by NEW. Then from the slope, we can get N. So when we get this N, it can be used for calculating magnetic field for a particular hole voltage. So just put in the values, you will get the magnetic field. Now, moving on to the next question. Here we can also use the concept of magnetoresistance, but if you don't know about that, then knowing these things is enough.